What's up, everybody? It is Mr. Boylan, and today we are going to explain how pH of aqueous solutions can be controlled with buffers. In this particular video, we're going to calculate the pH of a buffer solution. Now, as you take a look at your notes, you're provided with a quick example of pH calculation for a buffer solution. As you read there, it says calculate the pH of a buffer solution that is 0.05 molar in benzoic acid. You're provided the Ka value and 0.150 molar in sodium benzoate. Really exciting stuff. The very first thing I'm going to do, though, is throw down the equation that represents this buffer solution. And then I'm going to create an ice table. My initial concentrations are provided to me in the problem itself. Important distinction here between the pH calculations that we were doing for weak acids or weak bases and what we're going to see here in these buffer calculations. Recognize that we have a substantial concentration of the conjugate base. It was because we added this sodium salt. In the weak acid or weak base pH calculations, we didn't have a huge concentration of this because by definition, a weak acid or a weak base is not going to dissociate. It's not going to form these ions. So, big thing to watch out for there, we now have an initial concentration of our conjugate base. Woo! Our changes are going to come from the stoichiometric relationships that we see in the balanced chemical equation. And then we come up with our equilibrium concentrations based on the initial concentrations and those values we use to represent the changes. Now, as we look at the equilibrium constant for this reaction and plug in our equilibrium concentrations, an important assumption we're going to make here is the X is small approximation. In other words, we're going to say or recognize that the change in concentration from the initial concentrations of both our weak acid and its conjugate base are going to be so small as to be insignificant. It's that same idea as, you imagine you are standing on a balance, taking your mass or taking your weight, and then somebody hands you a penny. There is, in fact, a change in mass because you are now holding that penny. But unless you have a exceptionally precise balance, it's not going to record that change in mass. It's the same idea here because our concentrations, initial concentrations of the weak acid and weak base are going to be so much greater than the change, we can essentially drop them out of the calculation. And it makes our life a heck of a lot easier. And so if we solve for X, we come up with a value of 2.2 times 10 to the negative 5. Recall that X is our hydronium ion concentration. Since we know the hydronium ion concentration, you should recognize then that pH is solved for by taking the negative log of that hydronium ion concentration. So it's simply a matter of plugging that value into the pH equation and solving, we end up with a pH of 4.66. Now, as thrilling as that was, there's actually a much easier way to solve these problems if we continue with this X is small approximation, which we're going to do all of the time. There are some things that we should do to check, which we'll talk about in class, but for the most part, you can assume or make this assumption about the change in X all the time. So if we make this assumption about X, that it's going to be very, very small, again, I want you to think about the equilibrium constant for this equation or any equation. We can simply rearrange it and solve for the hydronium ion concentration, which is what we need when we're talking about pH. And for any equation, then you come up with this sort of general expression where the hydronium ion concentration is equal to your Ka times the ratio of the concentration of your weak acid to the conjugate base. So again, this works out because we make that X is small approximation. So now it's just a matter of plugging in the Ka value and the concentrations of your acid and conjugate base to solve for our hydronium ion concentration, and then plug it into the pH formula to solve for pH, which, wham bam thank you ma'am, is going to be 4.66. and that's how you calculate the pH of a buffer.